Alright, so we did another example of working with an actual confidence interval. And one thing that we talked about at the end of class last time was how sample size can impact the width of your interval. So one thing that can naturally follow from there is wondering, well, how big of a sample do I need? So we're going to talk about now how can I actually figure out a sample size based upon knowing a few different things. So the different things that I'm going to need to know. The first thing I'm going to want to need to know is what that margin of error is. Now what I mean by that is I want someone to be able to tell me how far off they are willing to be, right? That's what margin error is, tells us how far off. So I would need someone to tell me, I'm willing to be 2% off, but I don't want to be anything more than that. So I need someone to tell me how close they need to be. The other thing I need to know is how confident you want to be. So I need you to tell me up front, do you want to be 95% confident, or are you okay with only being 90% confident? So I need to know that number. So then I can actually find my sample size to meet those specifications. So if you tell me your margin of error, you tell me how confident you want to be, I can tell you how big of a sample you need to collect to make those things hold true. And the reason why I can do that is because the margin of error is this formula. So really I'm just going to take this formula and solve it for n. And in all reality, I really want my margin of error to be no bigger than that. So I could technically think of that as being a less than or equal to as my ultimate goal, but just for solving sake, we're going to leave that as an equal to. But when I solve this thing now for n, I will find that n needs to be at least as big as z over my margin of error, all squared, times p hat times 1 minus p hat. Again, all I'm doing is taking that formula and solve it for n instead. Now if we look at this formula, things I know. Margin of error, again, is something someone's going to have to tell me. How close are they willing to be, or how far off are they willing to be? Z is based upon that confidence level, right? That's the only thing that impacted Z when we constructed a confidence interval was that confidence. So 90 versus 95%, that's going to impact my Z. But notice the other thing I actually have to know is I need to know p hat. And if we stop to think a moment, would I know p hat? Well, p hat is the sample proportion, which is collected from our sample, which means that we would already have a sample size if we already have a sample proportion. So I can't calculate something from my data if I don't already have my data. So what can I do about this p hat if I'm trying to figure out my sample size before I'm collecting my data? The first thing we can do is we can use a sample proportion from a previous similar study. This happens quite a bit in businesses that maybe are doing the same thing year after year after year. So I could use my p hat from last year to help me figure out how big of a sample I should take this year. So it seems like a pretty reasonable idea to use for p hat. Now there are, of course, some times that you're doing something brand new and you don't have a p hat from a previous similar study. So the other thing that we can do is if we don't have any idea of what p hat is, we use a p hat of 0.5 or 0.50, 50%. Now the reasoning we do this is it results in the largest possible sample size. Or in a sense, it's going to kind of cover yourself. This is if you plug in the p hat of 0.5 into this formula, that's going to give you the largest possible n than if you plugged anything else in for p hat. So it's sort of like I'm going to cover my butt type idea. If I use 0.5, I'm going to have at least a big enough sample. I might have too big, but I will at least have enough data to guarantee my confidence and my margin of error. Alright, so let's actually do a couple of examples of this to see how those formulas apply. So our example 3. So if we wanted to estimate the proportion of people who believe in ghosts, we're trying to figure out how large of a sample should we take so that our margin of error is no more than 1% with 95% confidence. So it's telling me my margin of error is 1%. which is 0.01 in decimal form. I need to find my z. My z is based upon confidence level and that alone. So I'm going to use that 95% that they gave us in the problem. Remember, how confident you are is what goes in the middle. The other 5% we're going to split up into either side here. And our goal is to find that number. So we go to the table looking for everything to the left of that question mark. So if I take my 0.95 plus my 0.025, I get 0.9750. Then we're going to pull up our table. And this is where we're working backwards. So we're working on the inside of our table, trying to find the closest thing to 0.9750 that I can. And I actually find this one exactly. And then we work out to what row, 1.9, and what column, 6. So I put those together, and it gives me a z of 1.96. The other thing I need to know is p hat. So the first thing I would ask myself is, do I have a p hat from a previous similar study? Well, at least from what they've given me, I don't have any idea what p hat is. I have no idea what the percentage of people who believe in ghosts is. I'm not just going to make up a number. So I'm going to use my safe bet of using the 50% because I don't have a previous study to look at. Now that I have all my numbers, I can just plug them in to my formula here. So my n is going to need to be at least as big as z, which is 1.96, over a margin of error, which is 0.01, all squared. That's the easiest part for students to miss, is don't forget to square that number, times p hat times 1 minus p hat. Then it's just a matter of plugging that into your calculator. And for this one, we should get 9,604 people. So we need to sample at least 9,604 people. Alright, now what's good about doing something like this before you actually collect data is, I can do the math, and the math itself isn't that hard. This is where the researchers should stop and ask themselves, do I have enough time, do I have enough money to get the responses of 9,604 people? If yes, great, do it. If not, I need to worry about what I can compromise on. So if I can't sample that many people and I want to make my numbers smaller, I've got to look at the two things I can control, which I can control my margin of error and I can control my z. If I want to make this number smaller, I can either make the top number smaller. How I do that is I would have to lower my confidence. So instead of being like 95%, I might have to say I'd be willing to be 90% confident. Or I've got to be willing to be off by more. So if I want this number to be smaller, this number on the bottom would have to then be bigger. So maybe instead of being within 1%, I'd be okay with being within 2% instead. So by doing this beforehand, you can see if, yes, I can collect that much data, or what am I willing to compromise on if I can't collect that much data. Alright, for another example in this video, we're looking at a small study first that found that 80% of graduating seniors planned on going to college. Now we'd like to estimate P, and then we'll figure out how large of a sample should we take so that our margin of error is no more than 1.5% with 99% confidence. Alright, so first we know our margin of error is that 1.5%. We got to change that to a decimal, so we're going to divide that by 100%, so be careful of this one. That'd be 0.015 once you divide it by 100%. I need to find my z, which is again based upon that confidence level that shows up in the problem. So this time, instead of having 95% in the middle, I'm going to have 99% in the middle. That leftover 1% I'm going to split up onto either side. I'm going to go to the table looking for the total left to the question mark. So that 0.99 plus that 0.005. So I'm going to go looking for 0.9950 and find the closest thing I can. Which you find is 0.9949 and 0.9951. Both of them are the same distance away, so you pick either, we're good. And then I just got to figure out which row and which column that happens at again. So I'm going to have a z of 2.58. So we have that number now. The last thing I need to know is p hat. So the question is, do we have a previous similar study that I can use? Yes, this time I found that 80% in a smaller study plan on going to college. So I'm going to use that. And now that I have everything, I can plug those in to my formula. So my sample size will need to be at least as big as my z, which is 2.58, over my margin of error, which is 0.015, all squared, times p hat, times 1 minus p hat. And then we just have to do the math for that, which we should get 4,733.4. So unlike the one above here, this one turned out to be a nice whole number. This one didn't. And if that's one thing I do know about sample size, is that it does have to be a whole number, because I'm talking about graduating seniors. I can't sample 0.4 of a graduating senior. Now this is something where finally how I wrote this formula is important. This greater than or equal to part. So if I need to sample part of that person, I have to sample all of them. I don't care how small this number after the decimal point is. Even if it's like 0.01, I have to sample that entire next person. So no matter what this number is, your normal rounding rules will not apply. And this we're going to round up and say that we need at least 4,734 graduating seniors. So then I can finally interpret that and say we need to sample at least 4,734 graduating seniors. Again, these are always round up, and it's because of that greater than or equal to sign is there to remind you of that. Alright, so this would actually conclude all of the new stuff that's in this set of notes. So your next video has working a full example that takes all of the ideas that we've learned here in the one categorical variable part 3 about confidence intervals. So hopefully after that example, things will piece together a little bit better as well.